All right, good afternoon, everyone. Let's get started. Weather is changing. We have more snow coming our way, so just make sure you stay warm. And of course, enjoy snow. All right, so we have just finished our midterm exam. So quickly, so we have homework 1 to 5. These are our the only 5 homeworks. We're actually finishing the homework 5 grading today, so hopefully that should be ready either today or tomorrow. Please make sure you check your scores in Canvas, right? Also, we have feedbacks provided, so please check. One, of course, if you have any question regarding the grading, if there are errors or things that you're not sure, please reach out to your TAs regarding the grading question, okay? But also, please just check the common mistakes and also, of course, the specific feedbacks just to make sure, you understand how individual questions, are looking for and what the correct solution would be. If you have any questions, of course, talk to our TAs to come to my office hours. That's our just generally make sure you have a good understanding of the content of the course, okay? Midterm exam. We have finished the midterm exam. They are being graded. Well, after we finish homework 5 grading, we'll continue with midterm exam grading, okay? We probably will not be able to finish it this week, so I cannot return the graded exam this Thursday. Next week, I have the checkpoint, so it's probably after the next week when we return the exam copies. But once we finish grading, the scores will be posted in Canvas, okay? So the next thing, we're now switching gear a little bit, right? So we're now in week 11. Okay, next week, we're going to do our project checkpoint, okay? So if you look at our course project, I know we did the proposal, right? Why was it week 6? A few weeks back, right? So it's probably kind of every team is probably now kind of refreshing your memory a bit, right? Trying to check what do we propose to do, right? And check where things are. But hopefully with this week, right, you can all get together, review things that you have proposed, and see where things are, make any adjustments so that you're getting ready for the checkpoint, okay? So for the checkpoint, there are things that are similar. Will be the checkpoint slides, checkpoint report. So you have already submitted the proposal report and slides, right? So all you need to do is take that, update it, and you can just build from there. Because by the time you submit your final report, right, same thing, keep updating so that you have the full report, okay? So unless you're changing your project completely, right? Otherwise, you would be able to just take what you have already and expand on top of it, okay? So week 12 checkpoint, so we're basically doing something similar to our proposal week. So we're going to have meeting with individual groups. We're just really trying to see where things are and whether there are feedbacks we can provide right now, rather than waiting till the very end of the semester, okay? So we don't have many weeks left, right? So we're now in week 11. So next week's a checkpoint, and then we'll have another week of lectures, and then week 14 is a fall break, right? We don't have any classes. When we come back, we have 2 more weeks, right? Week 15, we have lecture. Week 16, we're doing the final project meetings, and we'll be done by then, okay? So we'll talk more about what you would do for the final submission, okay? But in the meantime, of course, the main thing is for the checkpoint, okay? So make sure you submit the survey, right? We're going to do the scheduling survey. It should be posted later today. And please finish by Thursday, okay? So that we can post the schedule on Friday, okay? One thing to note, okay? Please get together with your team members, okay? Check your availability and have just one team member submit the availability survey, okay? Because the last time for the proposal, we have team members, each of them submitting one, that's fine, but when they have conflicts, meaning that your submitted responses are not even consistent, it's really hard for us to schedule your whole, your team, okay? So please, right, as just a regular check-in, you as a team come in, come together, okay? Talk about where things are, what you want to continue doing for the project, but in the meantime, just find some common time slot that would work for the whole team and have just one team member submit the survey, okay? All right, so please do that. Finish the survey by this Thursday and watch out on Friday. So we'll be posting the schedule, okay? So of course, if there's any issue, let us know, but the plan is that for the whole team, right, to be meeting with us during the scheduled time slots, Okay, but also as a reminder, those meetings are really intended to be open to the whole class. Okay, so don't feel that you can only show up for your time slot. Okay, because we really want you to hear like other team members and our feedback, so that you get a better sense, right, of the things that you should be looking like watch out for and what kind of things you may be able to incorporate for your projects. Okay, all right. So that is one. Oh, actually, sorry, I need to actually update this timeline because I was talking to the TA about when this should be submitted, so I want to just make sure this is incorporated. So what we plan to do is that after you submit your report, right, checkpoint report, we want to make sure we actually have enough time to provide feedback before everybody leave town for the fall break, okay? So I was checking with the TA, so we are going to make it the Sunday, okay? So that'd be Sunday, 17th, if I get it correctly. Sorry, I should have updated sooner. And this again would be midnight. So it would be, so as I said, the idea is that we want to give you feedback based on your submissions before the fall break time. So I'm just doing this live right now. Just keep that note because we're going to plan our meetings all the way till Friday. But once you're like done with the meeting, or even actually before your meeting, you should be able to update your like slides and report anyway. Okay. So after you are meeting with us, you can incorporate the feedback to make some minor changes, hopefully, right? And then submit your report. And then our TAs will review your submissions, just to make sure. What is this? Let's see. Okay. All right. I think I got it right? So that's today's the 5th. Today is the 12th. Yes, okay, that is the 17th, the Sunday. Okay, so so what do you do for the checkpoint? Okay, so checkpoint is really just a way for us to kind of see where things are and whether there are any kind of challenges or issues we should address now rather than waiting till the very last week, right? So that's really the intention. So don't worry too much about, oh, we haven't finished, we have done a lot since the proposal. Of course, we want you to do more, but most important is we really want you to kind of switch gears, right? We have been working on the homework, we have been working on the midterm exam, but remaining coursework is really the project, right? Okay, so we want you to really kind of be focused on your project and really kind of making good progress, right, towards a good finish, okay? So as you are kind of like thinking about where things are, where you would like to finish, okay? Think about this, right? Of course, review your proposal. What do you propose, right? What kind of data you have? What kind of things you were thinking? But that was a few weeks ago. Now, giving your better understanding, right, of the problem and the more content we have covered in the course, do you want to update, right? You may have better ideas or there are other things you'd like to try. All those are fine. Okay, so that's why data mining is really exploratory, right? Usually you don't know upfront, right, exactly what you're going to do or what you're going to find, right? So it's a kind of iterative process, but you want to be able to thinking about your plan and update it, okay? So what has been accomplished so far by the checkpoint, right? We really want to make sure that you have the data you need. That's probably number one, right? Because if at this point you still don't have the data, you say, oh, I'm going to get it. But if there's any uncertainty, right, of your data access, that'll be very, very challenging, okay? So make sure you get the data you need, okay? Make sure you have, like, if you're using API to do whatever, right, you should have, right, if not all the data, most of the data, okay? And also if you're planning to use some kind of tools, some platforms, by now you should have at least have a concrete idea or reasonable confidence that this is going to work, right? Or I have a like very simple setup, but I know it's going to work for the larger set. That's fine, okay? But this is really about a lot about feasibility, right? What you know you can do or cannot do, okay? And also have a much better understanding or more concrete idea of what you want to accomplish or the things like different tasks you like to do, you like to try, okay? But also importantly, right? What remains to be done. That's important because ultimately we're looking at your project as a whole. It's like what do you have accomplished, right, in your course project, okay? So think about the different pieces, right, different components that you would like to accomplish and how they connect to each other such that when you finish, right, you have a way of summarizing what you have done in this course, but also really highlight, right, what you have learned, right? Because we, of course, want to see what you have done, say have done 1, 2, 3, but ultimately, data mining is about finding something interesting and useful, right? So what's the most important insights, right, you expect to be able to present by the time you finish, okay? The other piece is also important, right? What changes have been made? This is really important for you to think about. Is the proposal good? We just continue with that plan, or we have doubts, or there may be changes or things that we didn't expect right up front. For example, say, okay, our group actually have to change, our group membership may need to change, or our project may change to some extent, right? Either completely, or still have to shift the things around. Okay, that's fine. We allow that. You can make changes, right? But it's important, right? You don't wait. Okay, so think about what changes have been made, what changes you need to make so that you have a successful finish of the project. Okay, so that's what we're doing for the checkpoint, right? A lot, right? But hopefully with this week, right? This week is important, right? And of course, continuing for the remaining weeks, right? This is really we want you to stay focused. If you're working in a team, it is important for the team to be communicating. I know everybody's busy, right? We're probably just finishing multiple rounds of exams and then maybe have projects in other courses. Everybody has different schedules. It's hard, but it is important, right, for the team to communicate regularly, synchronize, and make sure everybody's contributing, okay? This is also a time when I actually start to hearing more issues or challenges, right? I understand not everything works out perfectly, right? If there are challenges, feel free to come talk to us, and we, of course, try to provide our suggestions and guidance, okay? But if there are issues or there are concerns, it's better that you talk to us earlier than later, okay? All right, so that's roughly, just keep that timeline for the checkpoint, okay? So I'm kind of reusing this slide. This slide I've been kind of using basically just as kind of general guidelines in terms of what do you want to be thinking about, right? And what we're looking for, okay? The main thing is about analytical thinking, okay? Reason about your work, right? We don't want to say just you put up a figure, say, okay, this is a figure. It has X and Y labels, okay? But what are we seeing? Why did you do this analysis? What do you learn from this particular analysis, right? And how will this motivate you to do something further, okay? So all the process, right? Whatever you're doing as you're putting up your report, as you're presenting your process, your results, always trying to explain, okay? So we decide to do this, or we decide to do this analysis, or we chose this model over the other one, or we're using those metrics, and based on the results, we're kind of concluding these things, right? So all those are things we're learning, okay? But with reasoning, and also always tie back to your motivation. Because I said your data mining projects intended to answer some interesting questions, right, for the problem setting you have picked, okay? So whatever analysis that you're doing, whatever model you're building, whatever results you're getting, see how that tie back to your problem setting, okay? So I was talking about subtasks, right? Well, how you, what kind of things you're trying to do, but ultimately it's about those subtasks, those hypotheses, right? Those analysis help you to answer some questions that may be of interest for that problem, okay? So keep that in mind, but also if you think about the whole pipeline, right? Understanding your data, so there's a lot, right? We talk about say, when you have your data, do some initial analysis, right? Trying to just have a general understanding of your data before jumping into, oh, I want to build a model to do classification, I want to build a model to do prediction. Yes, you can do that, but this initial round of analysis, right? Visualization actually can provide some very good insights. And this is actually a good, something we like to see for the checkpoint, because now you have your data, right? You have your problem setting. Go ahead and do some analysis and start trying to pull out some insights from your data, okay? Pre-processing, okay? So this is also important. Right now, if you have your data, hopefully you have done some checking, right? Because I remember having discussion with various teams about the potential, right, quality issues or things you may be able to do to make sure that the data is good, right? So think about, again, what kind of pre-processing may be needed or what you can do so that the data is ready for your actual modeling. Because otherwise you don't want to be, building the model and get really, either bad results or things are not working properly and then realizing the data you're using is just not what you intended, okay? Evaluation. So by now, hopefully you have a little bit more concrete ideas about what you want to evaluate, right? Because during the proposal stage, we're talking about, yeah, think about your problem setting, right? How do you claim success, right? What is important for you? Do you care about efficiency? Do you care about accuracy? Do you care about the error rate, right? Or is it false positive, false negative, right? All those are things that you want to now hopefully have a little bit more concrete ideas, right? And then as you are kind of doing your analysis, always include your evaluation, right? And as I said, with your evaluation, always include something that, okay, I have these results. What does it mean? What do I learn, right? Is it expected? Is it surprising? Or should I do something more given that? The other thing, smaller data to bigger data, right? If some of the team, if you have started, right, you may have realized, right, your data set can be like either too small or too big, right? We always say with the data mining, you want to have large enough data. Large enough meaning that it's manageable, right? It's reasonably efficient for you to kind of play with it, right? And try out different things, okay? If it's too small, that basically just say, okay, I think we try to provide feedback if we think our data is limited, right? But as you're working with your data, we say we need reasonable large data sets so that you're actually pulling out, right, interesting insights. But also, there are quite a few projects where your data can be too big, right? If you take everything, it's big, right? So that is where you say you want to start with a more manageable subset, okay? Because as you're just planning how you do it, writing out your code, having a reasonable size data set is very useful. You don't want to be running a very long process with a very large data set and realize, oh, I had a bug here, and now you have to kind of redo everything, or whatever you have spent, the effort is wasted, okay? So there's quite a bit of kind of reasoning, okay? Also, I think I talked to a few teams about how you can choose like a subset, right, or specific scenarios. For example, if you're doing this across like a longer time duration, or you're trying to maybe do comparison between different regions, right, start with one, so you know whatever you're doing, right, is working for that like subset, right. That also relates to like finish one pipeline before you augment. Okay, what we don't want to see is that towards the end is that you have all these pieces here and there, but you don't have anything like concrete to show. That'll be hard, right? We know that with the data mining, you're exploring things, right? You can always ask new things, but you want to show as you're building up, right, your components, then you have something you can show us to say that I have done this, this is something I'm getting, and how that is helping me or enabling me to do something further, okay? And a lot of teams had more like stretch goals, right? Because we know like other projects can progress at different things, and the things may not like always go as we plan. So having some stretch goals is very helpful, right? If you get to it, do it, right? So don't like feel like you have to say I'm done enough, I'm finishing now. I always encourage you to do more given the time you have, right? Because that's why data mining is interesting and actually useful, because you get to explore things that are just unknown, right? So but plan it so that for every subtask, every component, you have something you can show your effort. And if you're working as a team, really think about how the team members, either say you take this piece, I take that piece, we can work reasonably independently, or there'll be some kind of synchronized effort, right? So just make sure whatever problems you're working on, how you ever assign the task, right? The team members are kind of doing their part, and as a whole, the project is progressing. Okay. Towards the very end, as you submit a report, okay, finishing up your project, providing your executive summary, okay? By then, it's not just a list of, say, 1, 2, 3, 4, 5, we have done this, right? Executive summary is really, what's the highlight, right? So the highlight is what is the most significant thing you want to highlight about your project, okay? So we are asking, basically, this project, we're looking at this particular interesting and important problem. We did this kind of analysis and some of the key insights we have gained, right? I always use this kind of analogy, if you're only allowed to present, say, 5 slides, right? What will be on the 5 slides for your project? And if you have, say, more than 10 or even 20 tables, figures, you only get to present 3. Which 3 would it be? Right? Think about those things, right? What is the most significant? Of course, you will submit the full report, and you can add appendix so you can have more details. But it is important for you always to have this compact summary of what your data mining project has accomplished. Okay. Last but not least, I keep stressing, right? Teamwork. Okay. Teamwork is important. I hope like you actually benefiting from having a team to work with rather than, oh, I would rather work by myself, right? Because I do think this like shared ideas, like the brainstorming and actually really working together allows you to work on something of a larger scale and hopefully more interesting, okay? But ultimately it's about the team members working together, okay? So make sure you work effectively as a team, okay? And we will be looking at individual team contributions, so you don't like try anything like a free riders, right? You want to make sure you have your own items you can claim in the final report. It's like, okay, I have done this. Like even so, okay, I have like maybe 2 members join to work on that. That's fine, but at least you want to make sure you have bullets that you can claim as something you have like done within the team. Any questions? Very good. All right, okay. So of course, like our office hours, feel free to drop by, talk to us. So I'm happy to always talk about your projects, provide some ideas or feedbacks, okay? But questions, concerns also, yeah, feel free. Actually, yeah, don't wait, right? Come to us if you have any questions or concerns. All right. All right, so we are going to continue with our discussion of the main content, okay? So this is a quick review what we have covered in the previous weeks. So think about like from the very beginning, right? Very first lecture, we started talking about just, okay, what do we mean by data mining? What are we trying to do? What are the things we care about? Right? We talk about data mining pipeline. We talk about then like see how you address, like how you look at a problem, deciding whether it's interesting. And then we kind of started like with the pipeline, right? How you actually go from the raw data, trying to understand the data, trying to measure similarity, looking at some statistical information, pre-processing, and then we get to the data warehousing. It's about how you manage your data and how you actually can manipulate your data, the multi-dimensional data in different ways to support right, various kinds of analytical processing tasks, okay? We then started talking about some of the core techniques, right? Pattern mining, classification, cluster analysis, right? Those are broadly used, right, in like various kinds of data mining projects, and also something you should consider for your projects, right? How you can leverage what we have learned so far, right, to enhance and like address some interesting questions, right, for your problems. Okay, so we have really I'm trying to count, three more weeks of lectures. This is week 11, 13, and 15. Those are the 3 weeks we're going to have a bit more lectures, okay? So we have a few content to cover, okay? Chapter 10, deep learning. Okay, I know deep learning is very popular. There's a lot of research as well as like applied applications of it. We could probably spend the whole semester, or actually more than 1 semester, talking about deep learning. But we're trying to finish it, hopefully, while using 1 chapter and probably just 2 lectures to finish the discussion, okay? At a high level, this is the data mining course, right? It's not about deep learning, okay? There's a lot going on, right, in the field of deep learning. Okay, so generally in terms of machine learning research, more recent deep learning, there are some various techniques being investigated, and there are many application domains. From our purpose, right, we're focused on data mining. We want to really leverage the capabilities of deep learning because this is really powerful and can be very useful for a lot of our data mining projects. Okay, so as we're talking about some of the like concepts, some of the methods, right, really kind of tie back to your data mining problem setting. Okay. What are we trying to do, right, from the data mining point of view? Because with the deep learning, a lot of times it's like you have a specific scenario, right, and you're trying to learn certain things. Whereas mining is like a lot of times like, oh, I want to find the patterns, right? I want to build a model, so how some deep learning methods may be applicable. Okay, so this chapter is really intended as a high-level like introduction, but really like kind of tying back to like how this would be useful for data mining. Okay, so we start with some of the discussion of the basic concepts, and then we'll talk about how we can improve with training. Of course, deep learning models, like you all know, are very complex, right? So there's actually a lot of challenges, and also, of course, like approaches people are taking, trying to make the training process better. And then we look at some kind of like typical or like various types of deep learning or neural networks. Okay, convolutional neural networks, recurrent graph. Those, of course, are some of the major categories, and they're of course used in many different domains, but in very different ways, right? So you want to actually understand the capabilities, but also think about how that will be applicable for your problem setting. Okay. Starting point, of course, like nowadays, probably like you don't need to convince people that deep learning is really powerful. Okay, but what do we mean, right? So why do we care about the deep learning? It's because they're very successful, but why is that relevant, right, for us? Okay, so you cannot read all of this. This is from 2012. 12 years ago. So this New York Times article was basically talking about how scientists are seeing promise in deep learning programs. So back then, we have already seen actually a lot of progress in terms of so we're inspired by the series about how the brain recognizes, right, patterns. But then we're now using it to on what? Fields like computer vision, speech recognition, identification of a promising new molecules for designing drugs, right? So that's why earlier we see this more leading the kind of scientific field, right? And of course that continues to be, right? But then later on, of course, there's a lot more happening. Nowadays you can see deep learning used in many different things, okay? So this is 1 year later. I think this is from 2013. So the MIT Technology Review, they're basically looking about 10 breakthrough technologies. That's back in 2013. Of course, deep learning was listed as the ranking. That's the most influential one, okay? And now 10 years later, right, you probably have seen how much has coming out, right, and how much more progress we have seen. So just backtracking a little bit, right? So neural network is not new. Okay, even so, I think from the first edition of a textbook, we have been talking about neural networks. Or at the very beginning, people talk about data mining. We have been talking about the neural networks. Okay, but you will see there's a big change from the more of a classical neural network to the nowadays the deep learning approach. Foundation is still almost the same, right? So this is about think about how our brain works, right? So this is from the biological sense. You think about what is a neuron, right? You have the neurons. They're basically receiving input, right, from the other neurons through some kind of a combined effect, some activation, right? That then gets transmitted to the other ones. So that's the whole network, right? That's how our brain functions. Right? If you're, say, observing, just seeing something, hearing something, right? Recognizing some specific patterns, that is how our brain is leveraging all those neurons and the activation across those neurons to be able to trigger, right? Certain activities, okay? This seems complex, right? When I was reviewing this, I couldn't even explain individually what they are, but this is what in computer science, we try to simplify this, but still really capturing the core ideas, right? So going from this biological neuron, we're talking about this our abstraction, right? And how we're using this in a computing setting, okay? So at a high level, right, what we're looking at is that you have all kinds of inputs, right, or information that's being feeding, right, to you, okay? Once you have this information, but when you take this information, those weights, that's important, right? Going back to our ensemble discussion, right? When you're bagging, combining things, you view them equally. But in the real world, usually, you actually want to weigh them differently, right? So you may have different inputs, but you have different weights associated with them, okay? And now once you have this weighted impact, right? So that's a cumulative impact of multiple inputs with a corresponding weights. Now you need to act upon it, okay? So now we need to take that and then somehow make a decision about activation, okay? That's what we're trying to do, right? This is with one layer, okay? So with the idea of this the neuron or neural network, right? So at the earlier days, we have this idea of perceptual, okay? This was back in 1957, so that was quite a long time ago. So that's why I say neural network is not new, right? The idea has been around for a long time, okay? So back then, the idea is that, okay, so basically it's taking this like a perceptron, so it's taking the input, weighted sum, right? The original design doesn't even have the activation function. Basically just take the sum, weighted sum, okay? But what we have found to be useful is that one, you have this activation function, but also we're using a bias so that you can control, right, the threshold or how you're going to kind of like activate depending on the combined weighted value you have, okay? So this is the general process, right? So if you're talking about any kind of particular perceptron, right, you have your input information, you have the weight, you have the summation, you have the bias, you have the activation function. That's basically what you have, right? Those are the standard components or abstractions, okay? Of course, there are different ways for you to activate, right? Because the weights, of course, like the weighted sum seems to be fairly straightforward, okay? Bias is also something you can probably adjust. But the activation function, there has been actually a lot of research. And if you're seeing, like even nowadays, right, some of the newer research, people are still trying to play with, right, the activation function, okay? So some of the things, of course, like keep in mind, so there are just quite a few, right? But the high level is that you want to differentiate, right? So when you compute the weighted sum, you're then trying to make a decision, right, when you activate, right? So you're basically looking at some kind of threshold, and usually we're looking at some kind of nonlinear relationship, okay? This is just, in the real world, a lot of things is nonlinear, right? So we're using these nonlinear functions to be able to capture like different kind of properties, okay, when you're trying to decide, right, when to activate, okay? All right, so now you think about, right, so this is actually more of the classic view of neural networks, okay? So this is the prior pre-deep learning era. Let's think about how people think about neural network, right? So typically, of course, like you already have your input layer. Those are just the things that you kind of say, okay, these are the things I can observe, right? Okay, and then I have my output layer. Those are usually things I'm trying to decide, right? This could be like object detection or making decision, yes or no, or something, right? But then you would have the hidden layer, right? Hidden layer basically means, okay, I don't know what they are, but I'm trying to use that to help me to capture some of those kind of nonlinear relationship, okay? Utilizing the input layer. That's a simple thing. Later on, people add maybe a couple more layers. Okay, but at the high level, this is what you're looking at, right? So you have the input layer, hidden layer, output layer, and these are connected, right? You have this connected units. Okay, so you have this directional connection, right? Going from the input, going to, all the way to, starting from the input, going to the output. Okay, you have the weights associated with, meaning that the different connections, right? They may be weighted differently. Okay, depending like what you're trying to capture. Okay. It's a multi-layer design, and the seller, you always right, have input layer, output layer. You have at least one hidden layer, but usually more. But back then, early days when people work with neural networks, typically you work with a few hidden layers, okay? Mostly due to one, just the limited computation, right? It gets too complex very quickly. So back then, we just don't have that kind of computation capability, but also you don't have the efficient method to work with, right, a more complex neural network, okay? But still, some of the ideas are already there, right? So you have the feed forward, so that means once you have the input value, you can then propagate, right? You can propagate the information till you get to the output layer, okay? You also have the earlier design is fully connected because the idea is that, okay, I don't know, right? So I want to actually take all the information I can get and then decide, right, how I aggregate the information. Okay, so the initial design is fully connected. Okay, so at every layer, right, so you basically have an input from all the previous layers with the weights. Okay, back propagation, which we'll talk about more later, right? That's also the idea because you want to use your output value, right? Because remember, this is supervised learning. Okay, so you have your output value, and now you compare with your feed forward computed value, right, using your current weights. And see where things are different, right? And then now you go backwards, right? You're trying to adjust the weights, okay? So ultimately, you want to be able to have this network, like a neural network structure, and the weights be able to fit, right, the data you are being provided so that your model can actually provide a good approximation, right? Okay, so those are some of the key ideas when we're like just people start talking about neural network, and there has been actually a lot of like research on neural network. So this is just a link. This is a new one. If you haven't played with it, it's actually quite fun. Okay, so it's actually called a playground. Okay, you can go there, just play with different neural networks. Okay, and don't worry about breaking anything because you really can just try anything and you'll be fine. Okay, but now when you look at this, right, if you are to build this, what are the things you need to decide? If I ask you, okay, I have a data set, I have a problem setting, I'll ask you to go ahead and build a neural network. What are the things you need to decide on? Any ideas? Like if you just look at this structure? Like how many? Yes?
Like how many nodes and edges you should have in the network?
Yes. What is my network structure, right? That means how many nodes I have at each layer, right? Okay. And then how, of course, the weights will be decided or either initialized, adjusted, right? So those are like the basic things, right? That's why earlier days when people were playing with a neural network, right? You, in a way, you may have some idea you can try, but a lot of times it's really try and error. How will I know? Like in the hidden layers, it's like 2 versus 3. Or is it like the more the merrier? Maybe not. Would 3 be sufficient, or do I have to go to 5, right? So there's just a lot of, how to say, decision making, right, up front, and sometimes really just to try. That's why I say like a neural network, like in the classic setting, it has been successful. It has actually good performance, but it's not easy to work with. Okay, so here, number of layers, number of units in each layer, right? And then depending on like what you're working with, right? Continuous value, discretize, or how many classes you're dealing with. So you need to decide, right, your input layers and your output layers, okay? But then ultimately, right, it's about what do you do, right? So a lot of times we're using neural net to make like these classification decisions, right? So a lot of times just like how many classes. If you have binary classes, that's easy. You probably just need 1 unit, right? It's 0, 1 output, okay? Or if you have multiple classes, then you could have multiple like units, right, for your output layer so that you can capture, right, the different types of decisions, okay? So this is the main thing, right? So neural network has been around for a long time. People have tried it in many settings and have shown it actually works well. Okay, comparable performance with like some of the decision tree based or naive, or actually Bayesian belief networks, support vector machines. But for a long time, I think neural network was there. People try it, but it wasn't really, how to say, very popular or powerful. Okay. Largely due to, right, it's just not easy to work with, okay? It is a lot of try and error, and when you have reasonable performance, like it's hard to explain, okay? So this is actually something like you can ignore the details, okay? The textbook has more detail, but if you're interested, you can dive into some of the specifics of how you do the like weight adjustment, which is really the key part, right? Because with a neural network, you start with the initial design, you have your initial weights, but ultimately it's about how you adjust those weights, right? So that they can, right, give you a good model that would reflect, right, the training data you have, okay? But with the backpropagation, that's really the core idea, right? Because you have data, right, observable data from the input side. You have your network structure, you have the initial weights, you can easily propagate, right, all the way to the output layer, okay? But usually you don't get it like perfect, right, to start point, actually even after many runs. Always you're trying to approximate, right? So it's by the time you get to the output layer, that's when you can do the comparison to see how far you are. Either say, yeah, I got this, or like I got most of them, but I'm incorrect, or I'm actually pretty far, right, in those cases. And that is how you make adjustments backwards, okay? So the details I'll skip, okay? But the high-level idea, right? Propagate forward, compare the error, and then you back propagate the error so you can adjust the weights, okay? There are always some kind of termination conditions, like when you are done or when you're good enough, because a lot of that, this training can take time, right? And it's not guaranteed, right? We'll see later, right? There's really very difficult for you to say this is the global optimal, Okay, a lot of times you need some kind of like greedy algorithm. And this really gets to this one core challenge, right? And actually a lot of research has been and already is also still active. It's about how you learn those parameters, right? Because once you kind of like construct your neural network, right? With the data set you have, with the problem setting, with the metrics you care about, you basically want to train your model so that you can get all those parameters, right, to give you good results. Okay. So at a high level, right, you have your input, okay, usually a vector, right, multiple like input units. And then you have this kind of multi-layered network, which is pretty complex. They have a lot of parameters, right? And now you're trying to determine the parameters, right? So every time you have the predicted output, you compare with the ground truth, right? That's actually give you the idea of, like, say, there are actually two notions we'll talk about. One is the error, one is the loss function. Okay, so but generally, like, so you need a way to measure, right, how close things are. Okay, and then with that, then now you go back so you can make adjustments, right? That's the high-level process. Okay, this really then connects. You may have heard of this in different settings, and we actually mentioned this briefly earlier. Is about this gradient descent algorithm. Okay, number one. If you want to do a brute force search, that's usually not feasible, even with a like small-ish size network, because you have just too many parameters. Okay, and many of those are like continuous values, right? So it's almost impossible for you to try a brute force approach to figure out the optimal kind of like parameter settings. That's one. Okay. So that means you usually need some kind of greedy algorithm, okay? So gradient descent actually has been shown to be really useful and effective and efficient in many settings, okay? So the problem is simple in a way, right? As we said, like we have our training sample and we have the labels. All we need to do is that we need to use the difference, right, or the loss function to capture like ways to adjust our weights, okay? So with a gradient descent, basically you need a way to look at the gradient, right? And then look at the direction of the gradient so you can decide to how you want to adjust your values, okay? So once you have like feed forward, so you get this loss, right? And our goal, of course, to minimize one. Yeah, to minimize the loss of your model, right? So then you want to compute so that for every parameter, right? So basically you need a way to look at the gradient. This is really more like the slope, right? Whether like so basically give you a slope like how you want to go, in which direction, and how far you want to go. Okay. So with that, then you want to do the adjustment. Okay. So this is an illustration, right? In the general idea, right? If you have a kind of nicely, right, sloped function, then what you're getting is this, right? So you're trying to get, of course, this would be the global minimal. Great, right? So we're trying to get that point. So at any point, right, so you have a way of computing your gradient, and then in this case, like hopefully we can follow, right, those directions, those arrows, and get to the minimal, which is the optimal solution we're looking for, right? This is the best case. But it's not always that easy, right? In the real world, we actually see there are more challenges. Okay, so here, just like quick summary about like why neural network has been around for a while, but still people find it like what their pros and cons. Okay, the weakness is really about how much it takes to train it. Okay, so the training time is challenging parameters, right? Determined empirically. A lot of times it's really difficult for you to say what is the best architecture for you to run your network, and also it's not easy to interpret, right? So all those are challenges that have been limiting, right, the use of neural networks. Okay. But still, we're already seeing like why it's so useful, right? It's a high tolerance to noisy data. Okay, as I said, it has a lot of kind of internal kind of units through the weight process. Actually, you can actually handle, right? Nonlinear relations, very complex nonlinear relationships, and they are generally fairly robust to noises. Okay, and we'll see that, like especially for continuous valued data, they have been shown successful on quite a few settings. Okay, that's why like people continue to using it, right? And reach really also lead to the breakthrough later on. Okay, so now you think about it, right? So neural networks has been like used quite a bit, showing good performance, but usually in limited in scale and limiting is like adoption, okay? But what really like boosted, right, the significant jump from the classical neural network setting to the nowadays the deep learning setting. Okay, first with the deep learning, as the name suggests, right, we just have a lot more layers. Okay, so it's training deep neural networks with many layers. Okay, so because we have this much larger models, right, so we have more neurons, we have more layers, and we are able to capture some very complex information. Okay, so number one sounds great, right? Yes, we need a bigger model, but how do we make it happen, right? That actually has been the like roadblocks or the challenges all through these years because people have the ideas but just couldn't make it work effectively, right? But we know that, right? This is actually really important, okay? If you're interested in the history of deep learning, just look at some of the classical papers, and there's also some kind of comparisons, right? Because there were some significant kind of like benchmark kind of data sets and some classical tasks that people were showing how like improving the size of the model, but also improving the computation of those models, were able to show significant performance improvement. That has, of course, motivated, right, more research, and that's also a lot more active research and adoption has really enabled us, right, to really kind of like push the frontiers of deep learning significantly, okay? So number one, of course, is performance, right? If your performance is just comparable to other approaches and it's complex, that's why it has been around, but it hasn't been a lot of research, right? But it's only the earlier kind of like, say, deep learning work, really pushing the boundaries, showing how much you can gain, right? By like working with larger models and some more intelligent like methodologies and actually architecture design. Okay, also this is actually another thing a lot of people like, right? And actually it's important, right? So in the more like traditional, how to say, machine learning or like in the data mining too, right? So like you're trying to identify features, right? Remember we had so much discussion about your feature selection. You can actually extract your features, right? How you do some kind of feature engineering so that you're pulling out the most informative information from your data, right? Okay, but with the deep learning, the architecture, if you think about it, right? You have the input layer and you have multiple layers, but with all those weighted, like fully connected input, and then you have this kind of like nonlinear activation function. All those actually are helping you, right? It's kind of automatically extracting information that's most informative, okay? So that's actually make it actually a very useful, right? And also because of that, right, you can now build the end-to-end models, right? Remember we're talking about this kind of like feature engineering and model building being separate, right? Or you can do iterative, but now you actually have a fully integrated view because your model, the deep neural network by itself can extract the features, right? Do the feature engineering, and then help build a model for your downstream tasks. Okay, so great, right? So we know what deep learning, like deep learning is really about like a lot more larger models, and it can be very useful with better performance, much better performance, right? And actually is actually like doesn't require as much feature engineering effort to make that work. This is also what has really pushed things around, right? Large data sets. So you think about it, right? We always say like if you're trying to fit, right, like 2 parameters, right, you need how many instances to be able to like uniquely determine, right, the values of 2 parameters. But if you're talking about thousands, millions, billions of parameters, right? When you talk about large networks, right? You just need a lot of data. So a lot of information, a lot of data to even help you, right? To identify, like in this search space, right? Huge search space, things that may be like useful for your particular model, okay? So very large data sets, right? That's of course partly, I would say, or actually majorly contributed by the whole field, just the data, right? Data science, data analytics, data mining, because we are just everybody, right? Other domains, we're pushing more effort to get more data, right? Make more data useful. That's important. But now, not just you have more data, because you still need a lot of computation, right? To leverage the data to build your model, okay? So this really gets to the computation power, okay? So, but it's not just computation power. It's just also about intelligent ways, right, to do the computation, to make it even feasible and more efficient and scalable. Okay, so you need the data, you need the computation power, but then a lot of those, right? That's why like you actually have a pretty long list, right? Every day you probably like can get new papers talking about some like new ideas, right, in deep learning. Okay. There's a lot happening, okay? But it's really, I think it's interesting, challenging, but also exciting because you get to experiment, right? And reason about, right? A lot of new ways to design your neural network, okay? So when you look at any of those, right, it's not just, oh, there's another like deep learning neural network, right? Rather just, okay, what is unique about this one, right? What is the motivation example, or what is the usage scenario? Because why this particular characteristic or this particular like trick, right, may actually really be beneficial for this particular setting, right? That's why it's interesting. People are now looking at fundamentally, right, this new capabilities of deep learning, but really exploring a lot of innovative ways, right, to work with neural networks. Okay. So when we talk about, right, deep learning architecture, of course, like you start, for us, well, this is probably usually like a data mining view. We also look at the data view, right? What kind of data and then what it can do, like what kind of architecture you can use, okay? So of course, like many times you have multidimensional data, right? That's actually the core. Like a lot of data can be just abstracted as multidimensional data, okay? Then you would, so this is actually a lot in terms of this feed forward, right? That means like if you look at your input, the multidimensional data now naturally like correspond to the input layer units, and then through this like fully connected network, you kind of like propagate, right, your calculation and then adjust the results. But then also this more of the grid, right? So you think about, right, your data, images, of course, being the very good example, right? So why people want to actually use computer vision as actually one domain that really has been leading and driving a lot of advances in deep learning is because it have this kind of interesting, right, types of data. Okay, so you basically have grids, right? Think about those grid cells, right? Each like pixel in the image, right, have some value across channels, okay? And now you have some natural way of working with those kind of grid, and we'll be talking about, right, CNN. That's basically you can do convolution when you have those kind of grid data, okay? But then also, there's sequence data, right? Sequence data could be like text data, sentences, right? Actually, machine translation is another area, or speech recognition, right? It's another area where deep learning has been shown to be very powerful. Time series data, right? That's another one, or like some kind of like symbol, right? Sequence, like biological sequence, right? Many of those have not grid information, but this is sequential information. And with that, right, we now have neural networks that are actually embedding or incorporating this kind of sequential information, okay? And of course, graphs, right? When you have graphs, of course, it's not just one directional or this grid. You have all kinds of connections, right? So the graph neural network. So as you can see, right, there are many different types of neural networks, but instead of just trying to keep up, right, kind of learning one model after the other, really follow the reasoning, the motivation of all those kind of different designs, right? What kind of data you have, what kind of characteristic you see in your data, in your problem, right? And then given your knowledge of the different types of neural networks, right, do you see ones being more relevant and how you may be able to improve upon it? Or come up with a brand new design because your problem is like have some unique characteristics you can leverage. Okay, all right, so before we kind of talk about each of the like three main categories of neural networks, let's spend some time talking about training, right? Because we have said, right, deep learning models are big models. They have a lot of parameters, millions and billions of parameters, right? As a result, training those models is really important and challenging in many ways. Okay. So remember earlier we had this figure, like this nice kind of like a one, like a valley kind of a shape, right, for your gradient search. In that case, great, right? Your gradient search will be very effective, right? You quickly kind of like follow the slopes and get to the global minimum, which is your optimal solution. But in the real world, things are much more complex and usually messy, right? So this is just a way of illustrating what you may see in the real world. Okay, so in this case, right, okay, my global minimum is here, okay? If you visualize, of course, I know that's where I had to go, but if you think about how you're doing this, right, as you're looking at the gradient, okay? So apparently you have, right, different kind of local, like minimum, okay? Local means that they are lower compared to their neighboring positions, but they are still higher, right? So generally what we're trying to get to is this kind of low-cost local minimal, meaning that it's not a global optimal, but it's close enough, right? And doesn't take me too much effort to get to the global optimal, okay? This is what we're trying to get to. But you may end up at some of those places, right? Those are like high-cost local minimals. That means you stop there, you're thinking like this is the best, because with your gradient search, that's the point you'll be stopping at, right? And then say, okay, I'm done. But that actually end up being not the best solution, probably far from the best solution, right? And then you also have scenarios that you may have this kind of like a plateaus, kind of flat, and you may have a cliff, meaning a significant drop, or you could have this kind of saddle point, it's just kind of gradual, but still like after that, there's a pretty significant drop, right? So all this could happen with your training process, okay? So this is not easy, right? How do we find a good solution, approximate, like optimal solution, okay? Another thing that's also interesting and important, remember we're talking about overfitting, right? Overfitting means what? Overfitting is that you're spending a lot of effort training your model using the training data, right? You have a very nice performance there, but your model end up being too tailored for the training set you have. As a result, when you apply it to your testing set, because remember the idea is we should always separate, right? Your training process shouldn't be seen in my testing examples. Okay, so by the time you do your testing, you actually have like not so good, or actually the significant worse results. Okay, so that's really about overfitting. That means your model is doesn't have good generalization performance, right? Because that's really the difference. Because what we can do is using the training data, right, to build a model. But ultimately, what we want is be able to have a good performance in a general setting, okay? So that basically means you should intentionally, right, build your model and train your model in a way such that it's not too specific, okay? So these are the challenges, right? Both are very important, very challenging, because when you talk about large models, a lot of complexity in the data and in your problem setting, we really need effective ways. So if you look at some of the classical papers, right, talking about earlier, like how people actually dealt with, right, that's actually a lot of kind of insights, and a lot of actual research goes into it. And nowadays, if you just go ahead and use a model, you probably took it as granted, or we're doing this anyway. Everybody does it, but why, right? So let's look at some of the techniques, okay, that people have came up, right, to address this. First one is called this gradient vanishing problem. Remember when you're looking for, right, your optimal or local optimal, you're using gradient, right? This is basically the derivative, right? So your gradient will guide you, right, going like one direction or the other, okay? But the particular challenge, this is actually related to earlier, right? We mentioned the sigmoid activation function, okay? This is the definition. What you will see here is that when you have, because basically it's like this value is between 1 and 0, okay? So it is nonlinear. Actually, has nice kind of like range to work with many of the scenarios. But the challenge is when your output, right, this value gets too close to 0 or 1, right? If it's close to 0, 1, so that means you're on one end or the other, right? If it's too close, now you actually have, right, your derivative, which is here, right? If it's 1, that's almost 0, and if it's 0, that's the maximal on the other side. And similarly, if you look at your error, right, because this is 1 minus O sub j and O sub j. So this term, right, now becomes really, really small, because you have value that's very close to 0 or very close to 1. So either the value itself becomes very close to 0, or 1 minus the output becomes a very small value, okay? So if you look at this term, this O sub j times 1 minus O sub j, right? So when you're close to one end or the other, this term becomes very small. What does it mean? If your gradient becomes really small, that always like basically you don't have, like, so you think about it, right? You'll be at a place you're making very, very small adjustments, right? because you don't really have a good way to move one way or the other. You're kind of like stuck there, okay? So if your gradient is vanishing, what it means that you basically you're stuck there and you're not making progress and you're not finding, right, a better solution. Okay, so now once you know why this is happening, now of course we have a way to address it, right? So we just want to somehow like avoid, right, this very small gradient scenarios, okay? So ReLU, nowadays if you build a model, that's probably the default, one of the default like function we'll be using, right? It's called rectified linear unit, okay? All it's trying to do is basically just to adjust it such that we don't have this decay, like meaning that we're actually avoiding this gradient vanishing problem, okay? What is the definition simple, right? So you say if the output value is 0, if the value you calculate is greater than 0, I keep it. So this is actually the same as I. Otherwise, it's 0. So if you now do the derivative, right? So now then this would be 1 or it would be 0. So that means you would have a way of like, so basically you don't have this kind of middle ground where things get very small. So you say either 0 or you have 1, okay? This just allows us to basically either say, I can aggregate, because now if it's 1, that means I maintain everything, right, to the next layer. So that the next layer is when I aggregate, right, the previous layer values. But if it's 0, I just ignore it, right? I don't consider that unit. Okay, let me see if I have. Okay, and then there are actually a few other things. Okay, another thing is about this kind of learning rate. Okay, so remember with this gradient descent algorithm, right? You're finding a gradient, but there's also another mechanism, another parameter, which is the eta. This one. Eta basically controls how quickly you want to adapt, okay? So I mean, either like, so if eta, like say, either I make a big jump or I make a smaller kind of like adjustments, okay? So the original design, you use the same learning rate, okay? So the idea is that, okay, yeah, because I don't know what I'm looking for, but I'm using a particular stride, right, to look for, right, the optimal solution, okay? But it actually turns out that with that fixed learning rate, you actually run into a few issues, okay? One, your progress may be too slow because while you're taking this kind of small steps, right? It takes a long time. If you're far away from this optimal solution, it's taking forever for you to get there, right? So that's not what we want. Or you may actually jump over some areas that may have this kind of cliff, meaning that your best, like in this particular example, your design solutions are here, but if you jump too quickly, you get to the other one, you skip the whole area altogether, right? Or you can even also you can do this kind of oscillation. So that means again, it'll take you a long time to get it, or if sometimes you don't even get to that best point. Okay, so the high level thing is just that you want to be a little bit more adaptive, right? So it's like when you're searching for something, this is what I think about it in like real world, right? If you're looking for something, you may make a big strides, to start with, you can quickly get to an area that's probably more likely to have what you're looking for. And once you're getting there, you're getting closer, now you're making smaller, like getting kind of fine-grained search, okay? So that's the kind of idea, okay? So generally what we see is that you want to start, right, with some a value, usually bigger, and then you kind of gradually reducing. But how you reduce it, right? There actually quite a few different strategies. You may have a fixed, there's a fixed interval for you to reduce your learning rate, or you can actually look at the gradients you have used so far and try to kind of adjust your learning rate based on what you have done so far. Okay, there are also other ones to look at, not just what I've done so far, but also kind of see your neighborhood a little bit to see how things are spread out. Do you see big change or do you see some kind of gradual things? Okay, and also how close you are getting to the loss function, the optimal value. So there are actually quite a few interesting strategies, but the high level idea is that I want to be adaptive. So this adaptive learning rate actually has been there has been a lot of research, and still things you may be able to consider as you're working with your model and the training process. Another one, this is a term you may have heard out, okay? You may have heard about, and then the idea is very simple, okay? It's called a dropout. Earlier, as I was saying, like it's the overfitting, right? If you recall, like when we talk about decision tree, right? Remember, like if your decision tree overfitting means that you're building your trees that are getting too specific, right? You have many, many layers, okay? You have a lot of branches. You're basically getting a lot of very specific like scenarios, which may not generalize to your testing setting, right? So we say, well, let's prune a tree, right? So we want to cut out the branches when it's like enough, right? So with the neural network, there's some similar idea. It's about just, okay, I have the, like, instead of using the full connected neural network, let's just remove something. Remove some of the units and then remove the connections, okay? So that's the idea of dropout. Okay, so usually, of course, you need a way to control, right? How much, right? What percentage? So there's like dropout rate, right? You can do maybe, you can drop out half of it. You can do maybe somewhere between or more or less. But typically, this has shown to be quite effective. Why? Because we're making a model not as specific, right? In a way, we're forcing our model to be focused on things that are not too specific, right? Because if your model, like with those kind of removed units, you're still performing well, that means it's fine, I don't use that information, right? Or, yeah, I know those information a little bit noisy, but I'm still capturing the main kind of characteristics from my data. That's basically what this process is doing, right? The mechanism is simple, right? Randomly, like remove some of those components in your network. But it is really effective in terms of building your model to be more robust and more generalizable. Okay, another one, pre-training. As the name suggests, right? So instead of training the whole network as a whole, okay, I'm trying to stage my training, okay? Because with neural network, you usually have multiple layers, right? And we know, like with multiple layers, and if you're trying to fine-tune all the parameters at the same time, it's hard, right? So that means like you have, say, billions of moving parts you're trying to coordinate as you're trying to find the optimal solution, okay? So instead, the idea is that, okay, let's try to fix layer by layer, okay? That means I'm doing the pre-training, okay? So as my illustration shown here, right, so this is my original model, okay, which has a few layers, okay, and not too complex, but still has quite a few parameters, okay? So what I can do, right, so this is my first iteration. So that means I take the input, I have the output. I basically take the whole set here, right? No, actually the way I'm trying to read it. So this is 3 and 4. So basically I'm just considering, ignore this, right? I'm just using 3 and 4 as my hidden layer, one hidden layer, okay? So that is one model I'm training. Now it's much simpler, and hopefully I can train it quickly and find some reasonably good solution. Once I'm done, now I can fix, okay? So I fix this layer. So that means from U1, U2 to U3, U4. I fix it, okay? But now I'm now expanding, right? Because remember earlier I take U3 and U4, go directly to the output. But now I want to take U3, U4, but now I'm adding, right, the next round, next layer, okay? So U5, U6, U7, they are now being added. Again, I'm training this 3 layer, right? So now I'm using 3 and 4 as more of the input. We have the hidden layer, and then we have the output. Okay, once I'm done with that, same thing, right? I move 1 layer, done, okay? Now I have these first 2 layers being fixed. The red ones mean that, okay, their weights are fixed, and now I'm just like trying to train adding these 2 nodes and then training the remaining models, okay? So as you can see, right, computation-wise, it's much more efficient compared to training the whole model, okay? But also it has been shown that this pre-training is actually not only is efficient, but actually still give us very good results, okay? Because again, this is all about approximation, right? You're trying to look for a model that can help you to quickly identify the regions. And it turns out that like maybe once you fix the previous layer, that means they are sufficiently good in terms of extracting information that may be useful for the later layers. Okay? So that, again, pre-training, right? Simple idea, but has been shown to be very useful. Okay. A few more things. This one's called cross entropy. Okay, what does it mean? okay? This actually relates to the fact that whether we're doing regression or classification, okay? Earlier, like if you have learned regression, like early in the course, but also in other settings, right? Regression is trying to match, right? It's trying to match the values. So you're using this kind of like mean square error, sorry. So mean square is basically you're trying to do this kind of holistic fitting, right? Of the overall like distribution, okay? But if you're using this, right, for many times we're using deep learning for classification problems, okay? So classification problem, that means I care more about whether you get this 0 or 1 correctly, right? So if you go from, like, say, 0.9 to 1, I'm good, but I care less about it. It's just a 0.1 versus a 0.8, right? So it's more about whether you get your classification labels correctly or not, okay? So with that notion, now we're basically talking about, okay, with the mean square error, right, this is what we're doing, right? So the error is really like they're basically calculating how your observed value, right, is different, right? How far it is from 1 and the target on the other side. So you end up getting this mean square error as your loss function, okay? But this actually turns out to be not good as what we're looking for, right? So here, if you look at the red curves, okay, so this is a mean square error. So assuming, I think this is when we have, yeah, we're assuming currently I have a positive example. That means I want the target, right? The target value is 1. So I want my, like the model output to be 1, right? Okay. So in this case, right, so if it's like closer to 1, then I should have a 0. So that's great, right? So that means I have the error, right, or the loss function should be close to 0. But when we have something that's 0, that's also a small value. That's not what we want, right? Similarly here. So what I want is indeed instead of using this cross entropy, as you can see, okay? So this is the summation of the negative t, then log of O, okay? What this is actually showing us that you will actually now have this blue curves, okay? So what the blue curve is showing is that when it's 1, the positive, which is the case we want, right? Then I have this 0 value. That is the minimum I'm looking for. Great, right? But when it's far away, it's not 1. That means it's on the other side of the class label. Now I want to actually make it a small, like a larger value. So that means, no, this is not what I want. Incorrect, right? So now you have better, like you're stretching out, right, this different class label. This is for binary classification. If you have multi-class classification similarly, but the high-level idea is that when they're different from your class labels, you stretch it out, okay? One more, this one you also may have heard, right? This is an order encoder, okay? This one is quite different from the general setting of deep learning. Deep learning many times, actually for a lot of that research, is supervised, right? Because you need a way to have this output, right, the ground truth value, to compare with whatever you can compute to be able to adjust the weights, right? So that's a supervised learning. Okay, but later on, people actually came up with this very interesting idea and has been shown to be very powerful. It's called autoencoder. Okay, some of the projects are already talking about it, right, using autoencoder for your problems. So it's unsupervised, meaning that I just take the raw data, right, the data as is, but I don't have a label or something I'm trying to compare with. Rather, the goal is I want to take the original data, build a model, in a way kind of condense it, right? In a way you can view this as some kind of information like compaction or like dimensionality reduction, whatever. So I'm using a smaller model, hopefully, to capture the core information in the original data. And then when I reconstruct data using my model, I have a way, like I can reconstruct, I can reconstruct my original data with high accuracy. I mean, that's very close to what I see before. So that means whatever this smaller model encoder I have is actually capturing the core information. Make sense? Okay, so that's the high-level idea. Okay, so the process, right, is simple. Okay, and you can, of course, easily build up an autoencoder, but you will see, right, they actually can have really powerful mechanisms in terms of really just, like, say, finding a way, like the hidden layers, right? That's the model that's trying to capture the core information and the relationships, right, of your original data. So typically what you do is that you take an input layer, right? You have this encoder piece. That means like going through multiple layers so that you're kind of compacting things and extracting information. And then you get to, like, once you have this like encoded layer, now you're done. Now you're trying to decode. So that means now you want to expand, right? Reconstruct, okay? So the idea is that like, you are training your model and the weights such that, right, your encoder and decoder can like nicely map what you have as your original data, okay? So that's the idea. We're out of time, so we'll stop here. As I said, we started talking about basic concepts, how to improve it, and then we'll be going over the 3 types of neural networks next. Okay, that's all for today. Reminder, the survey, right? Checkpoint survey. Make sure you discuss among your team. One of you, please fill out the survey by Thursday so that we can have the schedule ready by Friday. Thank you.